In the summer of 2026, physicists at CERN made a discovery that sent shockwaves through the scientific world. The Large Hadron Collider detected strange particle behavior that could rewrite everything we know about physics. And this is not science fiction. This is real data from the most powerful machine ever built by humans. For over 50 years, the Standard Model has been the crown jewel of particle physics. It predicted the existence of the Higgs boson. It explained electromagnetism, the strong nuclear force, and the weak nuclear force. But the Standard Model has always had one giant problem. It cannot explain dark matter, it cannot explain dark energy. And now, deep beneath the border of Switzerland and France, a mysterious signal is suggesting the Standard Model might be outright wrong. The Large Hadron Collider is a 27-kilometer ring of superconducting magnets. It accelerates protons to 99.99% the speed of light. When these protons collide, they recreate conditions that existed just a fraction of a second after the Big Bang. Trillions of collisions happen every second out of this chaos. Physicists hunt for patterns. The LHCb detector is one of 4 massive experiments at CERN. It specializes in studying beauty quarks and charm quarks, particles that existed in the early universe but barely survive today. These quarks decay into other particles through specific pathways that the Standard Model predicts with incredible precision. Think of it like a factory that always produces the same ratio of red to blue widgets. The Standard Model tells us exactly how many red and blue widgets should come out. But in 2026, physicists at LHCb noticed something bizarre. The ratio was off. Specifically, in what scientists call charming penguin decays, electrons were appearing more frequently than muons. The Standard Model says electrons and muons are basically twins, and they should behave identically in these decays. Yet the data shows a 3.1 sigma deviation. That might not sound like much, but in particle physics, every sigma counts. At 5 sigma, a discovery is officially declared. At 3 sigma, physicists start losing sleep. And here's the kicker. This is not the first time this anomaly has appeared. Back in 2014, a similar pattern was seen in beauty quark decays. Physicists dismissed it as a fluke, but in 2022, the anomaly persisted. In 2024, it grew stronger, and now in 2026, it refuses to go away. The evidence is starting to mount. If this is real, it means a new force of nature may be interfering with these decays. Not the strong force, not the weak force, not electromagnetism or gravity. Something entirely new. A fifth fundamental force that has been hiding from us for billions of years. Some physicists are already speculating about leptoquarks, hypothetical particles that connect quarks to leptons. Others are proposing Z-prime bosons, heavy cousins of the familiar Z boson, that could carry this new interaction, and the most exotic possibility, a connection to dark matter itself. Imagine a hidden sector of particles that only interact with our universe through this subtle force. Dark matter would no longer be a mystery. It would be a neighbor sitting just out of reach. But let us pump the brakes for a moment. 3 sigma is exciting, but it is not proof. Particle physics has a long history of anomalies that vanished with more data. Remember the 750 GeV bump in 2015? It looked like a new particle. It was a statistical mirage. The scientific method demands patience. Extraordinary claims require extraordinary evidence. CERN is already planning the next run of the LHC scheduled for 2027. With higher luminosity, the collider will produce 10 times more collisions. If the anomaly survives that flood of data, the physics community will erupt. But even if it fades, this hunt is not wasted. Every anomaly teaches us where to look. Every dead end narrows the search. The beauty of science is that being wrong is almost as valuable as being right. Because when the Standard Model finally breaks, we will know exactly where to build its replacement. And that replacement could be the most profound shift in human knowledge since Einstein rewrote gravity. The Large Hadron Collider was built for exactly this moment. It was never meant to confirm what we already knew. It was built to break our understanding and force us to rebuild. And so what happens next? In 2027, the LHC will fire up again with more power than ever before. Physicists will watch the charming penguin decays with eagle eyes. They will compare electron rates to muon rates across millions of collisions. If the ratio stays skewed, the Nobel Prize race will begin. If the ratio normalizes, physicists will update their models and keep searching. Either way, the universe is speaking. We just need to learn its language. This is why fundamental physics matters. It is not just about particles and equations. It is about understanding the operating system of reality itself. Every smartphone, every GPS signal, every medical scan relies on quantum mechanics. The next breakthrough could unlock technologies we cannot even imagine today. A new force of nature could lead to new energy sources, new communication methods, or entirely new ways to manipulate matter. History shows that pure curiosity drives the biggest revolutions. Faraday discovered electromagnetism with no practical goal. Today, the entire modern world runs on it. The Higgs boson seemed useless when first proposed. Now it anchors our entire understanding of mass. So when you hear about a strange anomaly at CERN, do not think it is irrelevant. Think of it as the first crack in a wall that has stood for 50 years. Behind that wall might be an entirely new room in the house of physics, and we are standing at the door, key in hand, ready to turn the lock. Subscribe to Curioscope Global and turn on notifications, because when CERN announces the next update, you will want to hear it first.